All right, let's dive right in. We are going to tackle one of the most mind-bending, frankly weirdest ideas in all of science, quantum entanglement. It's a concept so bizarre, it actually freaked out Albert Einstein himself, who gave it a nickname you've probably heard. And over the next few minutes, we're going to unpack what it is, why it's so strange, and what it tells us about the very fabric of reality. So, here's how we're going to break this down. We'll start with a simple analogy that seems to make a whole lot of sense until it completely falls apart. Then we'll dig into Einstein's famous problem with it, see how physicists came up with a genius way to test it, and then we'll look at the shocking results from those experiments. Finally, we'll try to answer the big one. What does it all mean?
You know, the core question we're tackling today is one that pops up constantly, like in this Reddit thread that got us started on this whole thing. How in the world do two particles, separated by maybe light years, seem to know about each other instantly? Are they communicating? If so, how? That is the mystery we're here to unravel.
To get our heads around this, let's start with an idea that feels, well, normal. It's an analogy people use all the time to explain entanglement. But as you're about to see, it has a fatal flaw. And that flaw is exactly where the real weirdness of the quantum world begins.
Okay, so picture this. You have a pair of shoes. You put the left one in a box, the right one in another box. You shuffle them so you don't know which is which. You keep one, and you mail the other one to your friend on the opposite side of the planet. The moment you open your box and see a left shoe, you know instantly, faster than light, that your friend has the right shoe, right? There's a perfect connection. This part is simple, and it's not the mystery. But, and this is a huge but, that simple, common-sense explanation is just plain wrong. As this Reddit user nails it, the universe does not work like a pair of shoes in a box. The idea that the shoe was always a left shoe before you looked, that's what's called a local hidden variable. And experiments have proven, without a doubt, that this is not how reality works.
So this is the crucial point. The problem with the shoebox story is that it assumes the shoes had an identity, left or right the whole time. But quantum particles, they're totally different. Before you measure it, an entangled particle doesn't have a definite state. It's just sitting in a fuzzy cloud of possibilities. And that is where the real weirdness and a massive historical debate kicks off.
And you know, this wasn't just some quirky thought experiment. This was a full-blown battle for the soul of physics. And right in the middle of it was the most famous scientist of the 20th century, Albert Einstein, who thought this whole idea was just completely absurd. Einstein is the one who famously called entanglement spooky action at a distance. And that phrase just perfectly captures how much he disliked it. He just could not accept that measuring a particle right here could instantly affect another particle way, way over there. It seemed to break the cosmic speed limit, the speed of light, and the whole idea of cause and effect.
This whole thing just exploded into public view back in 1935. Einstein and his buddies Podolsky and Rosen published this famous paper about the paradox. It even made headlines. The New York Times ran a story saying Einstein attacks quantum theory. The physics world was torn, and another giant of the field, Niels Bohr, immediately fired back with his own paper. The battle lines were drawn.
So what was Einstein really fighting for? He was defending something called local realism. Now that sounds fancy, but it's basically just our everyday common sense. It's made of two parts. Realism is the idea that the shoe is a left shoe even when you're not looking. And locality is the idea that poking something here can't instantly affect something way over there. Our shoebox analogy? Pure local realism. So for Einstein, the logic was simple. If quantum mechanics leads to this spooky action, then the theory itself must be missing something. He was convinced it was an incomplete theory, that there had to be some hidden information, like the shoe's identity, that the theory just wasn't accounting for. For decades, this argument was just philosophical, a clash of titans. How could you possibly test it in a lab? Well, then a physicist named John Bell showed up and completely changed the game.
In 1964, John Bell had this incredible breakthrough. He found a way to take this philosophical argument and turn it into a real, testable experiment. He came up with a mathematical theorem that could actually tell the difference between Einstein's common sense world and the bizarre world of quantum mechanics. So, a typical Bell test looks something like this. You have a source in the middle that creates pairs of entangled particles. It sends one particle over to an observer we'll call Alice, and the other particle goes to an observer we'll call Bob. They're far apart, and they each make measurements on their particles, like checking their spin.
Now here's Bell's genius. He proved, with math, that if Einstein's local realism was true, if the world works like shoeboxes, then the correlations between Alice and Bob's measurements could never be stronger than a certain amount. There was a hard limit. But if quantum mechanics was right, the correlations would be stronger than that limit. It was a clear, unambiguous showdown. Run the experiment, measure the results, and you'll find out which version of reality we live in.
So, physicists built the experiments, they ran the tests, they measured the correlations, and the universe, well, the universe delivered its verdict.
And this wasn't some one-time thing. Starting with the groundbreaking experiments by a physicist named Alan Aspect in the early 80s and continuing with better and better tests for decades since, every single experiment has pointed to the exact same mind-boggling conclusion.
The verdict? Einstein was wrong. Quantum mechanics was right. Bell's limit has been broken again and again and again. Our common sense idea of local realism just doesn't work at the deepest level of reality. The spooky action is real. The universe is just weirder and more connected than we ever thought possible.
Okay, hold on. Before your brain runs off with ideas about sci-fi communicators, we have to bust the single biggest myth about entanglement. This spooky connection does not, I repeat, does not let us send messages faster than light. I know, it feels like it should, but it's a huge misunderstanding.
So why not? Well, it all boils down to randomness. First, the result Alice gets from her measurement is totally random. She can't force her particle to be spin up to send a 1 to Bob. Second, you only see the spooky connection after the fact, when Alice and Bob call each other up and compare their lists of results. Until they do that, Alice's data just looks like a random string of ones and zeros. And finally, Bob has absolutely no way of knowing when Alice has measured her particle. Nothing changes on his end, so no information gets sent.
So if local realism is out the window, and we can't use this to call our friends on Mars, then what does it all mean? What is the universe actually telling us about itself?
And this is the humbling part. While we know what happens, we still don't really agree on how or why it happens. There are all these different interpretations being debated. You have the many worlds idea, where the universe literally splits into parallel timelines with every measurement. You have others who just say, look, the universe is non-local, that's the rule, get used to it. And there are even wilder ideas, like superdeterminism, which says everything was locked in from the moment of the Big Bang. The jury is very much still out.
But no matter which interpretation you prefer, the key takeaway is absolutely profound. We have to let go of the idea of particles as just little independent billiard balls. At some fundamental level, reality seems to be this deeply interconnected web, a system where two parts can be linked as a single whole, no matter how much space is between them.
And really, that leaves us with one last, huge question to chew on. The universe has proven that our most basic, gut-level intuition about what here and there even mean is just wrong. So, if we're wrong about something that fundamental, what else about our perception of reality is just a complete illusion?